Hello. I hope you fall asleep quickly and sleep soundly. Let this boring story help you rest. Please don't forget to like and subscribe. I will have many more boring stories for sleep. The industrial synthesis of Portland cement begins with the strategic and large-scale exploitation of massive geological deposits, primarily consisting of calcium carbonate in the form of limestone, chalk, or marl. This initial phase represents the fundamental transition of terrestrial minerals into a standardized chemical precursor. The selection of a specific quarry site is governed by the exhaustive mineralogical profiling of the subterranean strata, as the final cementitious product requires a precise stoichiometric balance of calcium, silicon, aluminum, and iron oxides. In addition to the primary carbonate source, which provides the essential calcium oxide, secondary argillaceous materials such as clay, shale, or bauxite are procured to provide the necessary silica and alumina components. This procurement phase is characterized by a high-intensity mechanical intervention into the Earth's crust, an environment defined by the rhythmic operation of heavy-duty hydraulic excavators, the persistent hum of massive haul trucks, and the calculated application of explosive energy for primary fragmentation. The extraction process involves the systematic removal of the overburden, the layer of organic soil and non-essential rock that covers the targeted mineral deposit. Once the high-purity limestone face is exposed, a series of vertical boreholes are drilled into the rock at precisely calculated intervals using high-torque rotary or percussive drills. These holes are then loaded with a specific volume of ammonium nitrate-based explosive agents, which are detonated in a timed sequence to fracture the monolithic stone into manageable fragments. The logic of this blasting sequence is to achieve a specific fragment size distribution that optimizes the efficiency of the primary crushing station. The resulting rubble, known as run-of-quarry material, consists of limestone blocks that can vary in size from small pebbles to fragments weighing several tons. This raw aggregate is then loaded into off-highway haul trucks, which possess individual capacities exceeding 100 tons, and transported to the primary crushing facility located at the perimeter of the quarry. The mechanics of the primary mechanical crushing and compressive reduction. The primary crusher represents the first significant mechanical reduction of the mineral substrate. This station is typically equipped with a massive jaw crusher or a gyratory crusher, designed to reduce the run of quarry blocks into a more uniform aggregate size. In a jaw crusher, the stone is fed into a V-shaped chamber between a stationary steel plate and a moving, reciprocating jaw. The intense compressive force generated by the eccentric movement of the jaw systematically shears the limestone along its natural metallurgical planes of weakness. Alternatively, a gyratory crusher utilizes a conical head that rotates eccentrically within a larger bowl-shaped shell, crushing the stone through a continuous orbital grinding action. The objective of this primary reduction is to transform the disparate blocks into an aggregate with a maximum diameter of approximately 250 millimeters. The sound within the crushing department is a dense, cavernous roar, a combination of the mechanical vibrations of the heavy steel castings and the thunderous impact of falling stone. The process is governed by the absolute logic of mechanical advantage, where the electrical energy of massive induction motors is converted into the kinetic force required to overcome the internal crystalline bonds of the rock. Following the primary reduction, the material is transported via high-capacity belt conveyors toward the secondary crushing station. These conveyors often span hundreds of meters, winding through the industrial landscape of the facility. The movement of the crushed stone creates a persistent high-frequency rustle as the fragments collide and settle on the moving rubber belts. Secondary reduction and the achievement of granular uniformity via impact kinetics. The secondary crushing phase further refines the mineral aggregate, reducing it to a final size suitable for the milling and homogenization stages. This is often achieved using impact crushers or cone crushers. In an impact crusher, the limestone is struck by high-velocity rotating blow bars, causing the stone to shatter against heavy internal impact plates. This method is particularly effective for producing a more cubical grain shape, which facilitates better material flow in the subsequent silos and feeders. The output of the secondary crusher is typically a granular material with a maximum size of 25 to 40 millimeters. To ensure the technical purity of the material, a series of vibrating screens are employed to sort the aggregate by size. Fragments that exceed the specified diameter are recirculated back into the crusher via a closed-loop conveyor system, while the undersized material is directed toward the storage and homogenization piles. This logic ensures a high degree of dimensional consistency. During this stage, a primary chemical analysis is often conducted using online gamma-ray or X-ray fluorescence sensors mounted above the conveyors. These sensors monitor the concentrations of CaO, SiO2, Al2O3, and Fe2O3 in real time, allowing the facility to adjust the ratio of limestone to clay at the very beginning of the process. This level of technical oversight is essential for the eventual stabilization of the kiln chemistry and the prevention of fluctuations in the final clinker. Pre-homogenization and the logic of chevron stockpiling. The final sequence of the extraction chapter involves the systematic organization of the crushed minerals into massive pre-homogenization stockpiles. Because the geological composition of a quarry can vary significantly from one section to another, the raw materials must be blended to achieve a uniform chemical baseline. This is achieved by the application of the chevron or windrow methods within a massive longitudinal storage hall. A long-traveling stacker moves back and forth along the length of the hall, depositing the crushed limestone and clay in thin, overlapping horizontal layers. This creates a massive elongated pile that contains thousands of individual layers of material, each representing a different section of the quarry. When the material is required for the next stage of production, a specialized reclaimer, typically a bridge-mounted scraper or a bucket wheel reclaimer, cuts through the vertical cross-section of the pile. By slicing through all the horizontal layers simultaneously, the reclaimer effectively blends the various mineral qualities into a single homogenized stream. This process is a study in industrial statistics where the natural variability of the Earth's crust is smoothed into a predictable technical precursor. The atmosphere within the storage hall is one of quiet, monumental organization, where the only movement is the slow, unyielding progression of the reclaimer across the face of the mineral stack. The mechanics of the reclaimer involve a series of scraper blades or buckets that drag the material towards a central discharge conveyor. The sound of this operation is a rhythmic, low-frequency scraping, a subtle mechanical counterpoint to the distant roar of the primary crusher. The reclaimer's velocity is managed by a centralized control system that ensures a constant mass flow rate, measured in thousands of tons per hour. This stability is a fundamental requirement of the manufacturing logic, as any interruption in the material supply would compromise the efficiency of the downstream milling and burning processes. The state of the raw materials at the conclusion of this first chapter is one of transition. The monolithic limestone of the quarry has been systematically fractured, crushed, screened, and blended. It is no longer a geological feature. It is an industrial aggregate possessing the uniform size and homogenized chemistry required for the intense thermal and chemical modifications that follow. The steady hum of the conveyor belts and the distant roar of the primary crusher remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the mechanical force required to prepare the earth for the synthesis of cement. The mineral aggregate is now ready for the raw milling department, where it will be pulverized into a fine powder known as raw meal. This transition from granular solids to a fluid-like powder is the next logical step in the manufacturing cycle, marking the end of the mechanical reduction phase and the beginning of the precision chemical preparation. The progression of the crushed mineral aggregates from the pre-homogenization storage piles into the raw milling department represents the critical transition from granular solids to a fluid-like powder known as raw meal. This phase is governed by the principles of comminution, where mechanical energy is utilized to overcome the internal crystalline bonds of the limestone, clay, and iron ore particles. The primary instrument of this transformation is the vertical roller mill, a massive engineering assembly characterized by a rotating grinding table, hydraulic pressure rollers, and an integrated high-efficiency air classifier. The environment within the milling department is defined by a deep, low-frequency vibration that resonates through the reinforced concrete foundations, a pervasive layer of fine mineral dust, and the rhythmic cycling of the high-pressure hydraulic lubrication systems. The objective is to achieve a specific surface area, or Blaine value, that ensures optimal reactivity within the kiln while maintaining a strictly controlled chemical modulus. The vertical roller mill operates on the principle of interparticle crushing within a stabilized bed of material. The crushed limestone and secondary components are introduced into the center of the rotating table via a triple-gate rotary airlock, which is designed to prevent the ingress of ambient air into the pressurized milling circuit. As the table rotates at a precisely calibrated velocity, typically ranging from 20 to 35 revolutions per minute, the centrifugal force drives the mineral aggregate outward toward the grinding track. Here, the material is trapped beneath a series of large-diameter rollers, which are manufactured from high-chromium wear-resistant alloys. These rollers are not driven by independent motors, but rotate through frictional contact with the moving material bed. The mechanics of hydraulic compaction and material bed stability. The mechanical force required for pulverization is generated by a manifold of hydraulic cylinders that apply a massive vertical load to the roller assembly. This load, which can exceed several hundred tons per roller, induces a state of extreme compressive stress that fractures the mineral grains. The thickness of the material bed on the grinding table is monitored by high-sensitivity displacement sensors, which provide real-time data to the hydraulic control system. If the bed becomes too thin, the system reduces the pressure to prevent direct metal-to-metal contact between the rollers and the table. If the bed becomes too thick, the pressure is increased to maintain grinding efficiency. This constant adjustment is a study in industrial stability, ensuring that the energy consumption per ton of material remains within the specified parameters. To facilitate the movement of the ground material, a small volume of water is sometimes injected onto the grinding table. This moisture helps to stabilize the material bed and prevents the fluidization of the fine particles before they can be captured by the airstream. The sound of the grinding process is a continuous earth-shaking rumble, a manifestation of the massive energy being dissipated as the crystalline structures of the limestone and shale are decimated. The dynamics of air-swept material transport and classification. The vertical roller mill is an air-swept system, meaning that the transport of the pulverized material is achieved through the movement of a high-velocity gas stream. A massive centrifugal fan, powered by an electric motor of several thousand kilowatts, draws hot gases through the mill from the bottom upward. These gases are often sourced from the kiln exhaust or the clinker cooler, providing the thermal energy required to dry the raw materials, which may contain up to 15% moisture as they are being ground. As the mineral particles are fractured on the table, they are picked up by the rising gas stream and carried toward the top of the mill, where the dynamic air classifier is located. The classifier consists of a rapidly rotating cage equipped with hundreds of vertical vanes. The logic of the classification process is based on the balance between centrifugal force and aerodynamic drag. Coarse particles. Larger fragments that possess higher mass are thrown outward by the centrifugal force of the rotating cage. They strike the internal housing of the mill and fall back onto the grinding table for further reduction. Fine particles. Particles that have reached the required fineness, typically measured as a residue of less than 12% on a 90-micron sieve, are carried through the classifier vanes by the gas stream. The velocity of the classifier cage is adjusted via a variable frequency drive, allowing the facility to fine-tune the particle size distribution of the raw meal. The sound within the upper section of the mill is a high-pitched aerodynamic whistle produced by the movement of the dust-laden air through the vanes. This acoustic signature is a constant indicator of the mill's operational equilibrium. The concurrent with the physical pulverization, the chemical composition of the raw meal must be stabilized with absolute precision. This is achieved by the use of an online X-ray fluorescence analyzer, or XRF, mounted on the conveyor line or integrated into the air-swept ducting. Every minute, the analyzer bombards the moving stream of powder with high-energy X-rays, measuring the characteristic secondary radiation emitted by the atoms of calcium, silicon, aluminum, and iron. This data is transmitted to a centralized process control system, which applies the principles of the lime saturation factor, LSF, the silica modulus, SM, and the alumina modulus, AM. The control logic manages the feeder speeds of the individual raw material bins located upstream of the mill. If the analyzer detects a decrease in the calcium oxide concentration, the system automatically increases the speed of the limestone feeder. If the silica modulus deviates from the target of 2.5, the ratio of clay to sand is adjusted. This closed-loop control ensures that the raw meal entering the homogenization silo possesses the exact stoichiometric ratio required for the complex clinker-forming reactions. The environment of the control room is a stark contrast to the dust and noise of the mill, characterized by the quiet hum of computer servers and the steady flicker of data trends across high-definition monitors. Dust collection and the logic of high-capacity baghouses. Once the fine raw meal exits the classifier, it must be separated from the gas stream. This is achieved by a series of high-capacity cyclones and a massive pulse jet baghouse. The baghouse contains thousands of individual filter bags manufactured from heat-resistant synthetic fibers. As the dust-laden air passes through the bags, the raw meal is captured on the exterior surface, forming a dust cake that further enhances the filtration efficiency. At regular intervals, a burst of compressed air is injected into the top of the bags, causing them to flex and shed the collected powder into the hoppers below. The movement of the raw meal from the baghouse hoppers to the storage silos is managed by a network of air slides and bucket elevators. An air slide is a rectangular chute with a porous fabric floor. Air is introduced into the lower chamber, fluidizing the powder and allowing it to flow like a liquid down a slight incline. This method of transport is exceptionally efficient since it eliminates the need for moving mechanical parts and minimizes the risk of material degradation. The sound of the air slide system is a gentle, persistent hiss, a subtle undertone to the deep roar of the primary mill fan. The principles of gravity-based silo homogenization. The final sequence of the raw milling chapter involves the storage and homogenization of the powder in a massive concrete silo, often referred to as a continuous flow silo. Despite the precision of the online analyzers, minor fluctuations in chemistry can still occur. To eliminate these variations, the silo utilizes a complex internal aeration system. The floor of the silo is divided into multiple hexagonal or triangular segments, each equipped with independently controlled aeration pads. By aerating different segments of the silo at different pressures, the material is forced into a state of controlled fluidization. The raw meal in the highly aerated zones expands and flows upward, while the material in the less aerated zones subsides. This creates a massive, slow-motion churning effect, resembling the convection currents in a boiling liquid that blends thousands of tons of powder into a single, chemically uniform mass. The logic of the homogenization silo is one of statistical smoothing, ensuring that the kiln is fed with a material of absolute consistency. The atmosphere at the top of the silo is one of monumental stillness, where the only movement is the slow, silent rotation of the ultrasonic level sensors. The state of the minerals at the conclusion of this second chapter is one of functional readiness. The raw aggregates have been. The progression of the homogenized raw meal from the storage silos into the intake of the preheater tower represents the transition from mechanical preparation to the initiation of high-temperature chemical synthesis. This phase is governed by the principles of countercurrent heat exchange, where the cold mineral powder is brought into direct contact with the incandescent exhaust gases ascending from the rotary kiln. The preheater tower is a massive vertical structure, often exceeding 120 meters in height, containing a series of 5 or 6 centrifugal cyclones arranged in a vertical manifold. The environment within the tower is a study in extreme thermal gradients and aerodynamic turbulence, defined by the low-frequency roar of gas combustion, the rhythmic cycling of pneumatic cleaning cannons, and the intense infrared radiance emitted from the refractory-lined vessels. The objective of this stage is to elevate the temperature of the raw meal from ambient levels to approximately 900 degrees Celsius, facilitating the endothermic dissociation of calcium carbonate into calcium oxide and carbon dioxide before the material enters the kiln. The movement of the raw meal begins at the apex of the tower. The powder is introduced into the gas duct connecting the top 2 cyclones via a specialized splash plate feeder. This device ensures that the meal is uniformly dispersed into the high-velocity gas stream, creating a dense suspension of mineral particles. As the gas-solid mixture enters the first cyclone stage, the tangential velocity of the gas induces a centrifugal force that drives the heavier mineral particles toward the outer walls of the vessel. The particles then descend by gravity through a conical hopper and a series of flap valves into the next lower stage, while the cooled gas exits through the central vortex finder and is directed toward the raw mill or the dust collection system. The dynamics of gas-solid heat exchange and aerodynamic suspension. The logic of the multi-stage preheater is based on the maximization of surface area contact between the mineral powder and the hot gases. Because the raw meal is pulverized to a fineness where a significant portion is smaller than 90 microns, the total surface area available for heat transfer is immense. In each cyclone stage, the heat exchange occurs almost instantaneously, with the powder absorbing thermal energy as it remains suspended in the turbulent gas stream. The temperature of the material increases in discrete increments as it descends, from approximately 60 degrees Celsius at the intake to nearly 800 degrees Celsius by the time it reaches the penultimate stage. The thermal energy for this process is supplied by the exhaust gases of the rotary kiln, which enter the base of the preheater tower at temperatures exceeding 1,100 degrees Celsius. This recovery of waste heat is a fundamental requirement of modern industrial thermodynamic efficiency, significantly reducing the total fuel consumption of the plant. The management of the gas velocity is critical. If the velocity is too low, the powder will fall through the gas stream without adequate heating. If it is too high, the pressure drop across the tower will increase exponentially, requiring excessive electrical energy for the primary induction fan. the pre-calcination phase and the chemical dissociation of calcium carbonate. The most energy-intensive chemical transformation in the entire cement manufacturing process occurs within a specialized vessel located at the base of the preheater tower, known as the pre-calcinizer. While the upper cyclone stages serve primarily as heat exchangers, the pre-calcinizer is designed to facilitate the chemical decomposition of the limestone component. This process, technically referred to as calcination, involves the thermal dissociation of calcium carbonate, CaCO3, into solid calcium oxide, CaO, and gaseous carbon dioxide, CO2. This reaction is highly endothermic, requiring a constant and massive influx of thermal energy to maintain the necessary temperature of 850 to 900 degrees Celsius. To supply this energy, a significant portion of the plant's total fuel, which may consist of pulverized coal, petroleum coke, or alternative waste-derived fuels, is injected directly into the pre-calcinizer. This fuel, which may consist of pulverized coal, petroleum coke, or alternative waste-derived fuels, is combusted within the upward-flowing gas stream. The combustion occurs in the presence of tertiary air, which is high-purity, preheated, oxygen-rich air drawn directly from the clinker cooler via a specialized large-diameter duct. The logic of the pre-calcinizer is to achieve a degree of calcination exceeding 95% before the material even enters the rotary kiln. This effectively decouples the chemical decomposition from the subsequent sintering process, allowing for the use of shorter, more efficient kilns and a substantial increase in production capacity. The sound within the pre-calcinizer area is a deafening, continuous explosion, the acoustic manifestation of high-velocity combustion and gas expansion. The pressure within the vessel is carefully modulated to ensure a stable flame front and a uniform temperature profile. If the temperature falls below the calcination threshold, the reaction will cease and the kiln will become cold. If the temperature exceeds the specified limits, the mineral powder may begin to soften and stick to the refractory walls, leading to a catastrophic blockage known as a buildup. Refractory integrity and the management of volatile cycles. The internal surfaces of the preheater cyclones and the calcinizer are lined with high alumina or silicon carbide refractory bricks and castables. These materials must withstand not only the extreme temperatures, but also the abrasive force of the high-velocity dust stream and the chemical attack from volatile elements. In any industrial cement process, trace amounts of chlorides, alkalis, and sulfur are present in the raw materials and fuels. These elements volatilize in the high-temperature zone of the kiln and travel upward into the preheater tower, where they condense onto the cooler mineral particles. This creates a volatile cycle that can lead to hard crystalline deposits in the narrowest sections of the gas ducts. To manage this risk, the preheater tower is equipped with an array of high-pressure air cannons. At regular intervals, these cannons discharge a massive volume of compressed air into the vessels, creating a shock wave that dislodges any accumulated material from the refractory walls. Additionally, a bypass system may be utilized, where a portion of the kiln exhaust gas is extracted and rapidly cooled to remove the concentrated volatile elements before they can circulate back into the tower. The sound of the air cannons is a rhythmic, percussive thump that echoes through the steel structure of the tower, a mechanical reminder of the constant battle against material buildup. The final transition and entry into the rotary kiln. As the material completes its descent through the final cyclone stage, it has been transformed from a cold, inert powder into a highly reactive, incandescent substance. The calcium carbonate has been almost entirely dissociated, leaving behind a calcinized meal dominated by calcium oxide. The material is now at a temperature of approximately 900 degrees Celsius and is ready to enter the most iconic component of the cement plant, the rotary kiln. The transition is achieved through a refractory-lined chute known as the kiln inlet. The mass flow of the material is monitored by a specialized impact plate flow meter, or a loss in weight feeder, ensuring that the kiln is supplied with a perfectly constant stream of meal. The state of the minerals at the conclusion of this third chapter is one of chemical readiness. The geological bonds of the limestone have been broken, and the material is poised for the complex mineralogical syntheses that occur in the burning zone. The steady roar of the calcinizer and the rhythmic thumping of the air cannons are the constant acoustic backdrop to this industrial evolution, a testament to the scale of the thermodynamic force required to transform the earth into a building material. The material is no longer merely a powder, it is a thermal torrent, flowing downward toward the intense white-orange heat of the kiln, where the final transition into cement clinker will take place. This movement from the vertical domain of the preheater to the horizontal, rotating domain of the kiln is the next logical step in the manufacturing cycle, marking the end of the pre-processing phase and the beginning of the sintering climax. The entry of the incandescent pre-calcined raw meal into the inlet of the rotary kiln marks the transition from the vertical gas-suspended heating phase to the horizontal gravitational sintering phase. The rotary kiln is the central reactor of the cement facility, a monumental steel cylinder that can exceed 100 meters in length and 6 meters in diameter. It is positioned at a slight inclination, typically ranging from 3 to 4%, and rotates slowly at a velocity of 3 to 5 revolutions per minute. This combination of rotation and slope facilitates the continuous longitudinal movement of the mineral mass toward the discharge end. The environment within the kiln is the most extreme in the entire manufacturing process, defined by a white-orange radiant heat that reaches 1,450 degrees Celsius, the massive mechanical torque of the drive motors, and the complex fluid dynamics of a multi-phase material flow. The objective of this stage is the complete mineralogical transformation of the calcined meal into a hard, nodular substance known as clinker. The mechanical structure of the kiln is a study in heavy industrial engineering. The steel shell, which is several centimeters thick, is supported by a series of massive forged steel rings known as tires or riding rings. These tires rest on heavy-duty support rollers equipped with hydrodynamic bearings that manage the immense weight of the rotating assembly, which can exceed 2,000 tons. The internal surface of the shell is lined with high-specification refractory bricks, designed to withstand both the extreme temperatures and the chemical attack from the molten minerals. In the lower sections of the kiln, known as the burning zone, specialized basic bricks made of magnesia spinel are utilized, as they possess the unique ability to allow a protective layer of solidified clinker, the coating, to adhere to their surface. This coating is critical for the thermal insulation of the steel shell and the longevity of the refractory lining. The progression of thermal zones and the formation of bellite. As the material travels through the kiln, it passes through several distinct thermal zones, each facilitating a specific sequence of chemical reactions. In the upper, cooler section of the kiln, the calcining zone, any residual calcium carbonate that was not dissociated in the preheater tower is fully converted into calcium oxide. As the material continues its descent and the temperature rises toward 1,000 degrees Celsius, the first significant mineralogical synthesis occurs. The calcium oxide begins to react with the silica provided by the clay and sand to form dicalcium silicate, a mineral technically referred to as bellite or C2S. The formation of bellite is a solid-state reaction where the ions migrate across the boundaries of the mineral grains. This process is relatively slow and results in a material that is still powdery and granular. The sound within this section of the kiln is a soft, continuous rustling produced by the rolling motion of the mineral bed against the refractory bricks. The atmosphere is thick with dust and the hazy shimmer of intense heat. At this stage, the material is preparing for the most critical transition, the appearance of the liquid phase. The sintering climax and the synthesis of alite. The functional heart of the kiln is the burning zone, where the material is subjected to temperatures between 1,350 and 1,450 degrees Celsius. At this threshold, a portion of the mineral mass, approximately 25%, undergoes a phase change into a viscous liquid. This liquid consists primarily of melted aluminum and iron oxides, which act as a flux, lowering the reaction temperature and facilitating the final mineralogical synthesis. In the presence of this liquid phase, the previously formed bellite reacts with the remaining free calcium oxide to form tricalcium silicate, the primary strength-giving component of cement known as alite, or C3S. This process, known as sintering or clinkerization, is exothermic, meaning it releases a significant amount of thermal energy as the new crystalline bonds are formed. The appearance of the liquid phase also causes the material to aggregate, transforming the fine powder into hard, gray, marble-sized nodules. The thermal energy for this synthesis is provided by a massive burner pipe extending into the discharge end of the kiln. This burner creates a high-momentum flame that can be 10 to 15 meters in length, utilizing a combination of primary air and high-velocity fuel injection. The fuel, often a mixture of pulverized coal, petroleum coke, and alternative waste materials, is combusted in a highly turbulent environment to ensure a stable, concentrated flame front. The logic of the burner management is to maintain a short and sharp flame that maximizes the radiant heat transfer to the material bed while preventing the overheating of the kiln shell. The sound of the burning zone is a deafening, continuous roar, a manifestation of high-energy combustion and the gravitational tumbling of the heavy clinker nodules. Thermodynamic heat transfer and the logic of kiln shell cooling. The management of the thermal energy within the kiln is achieved through three primary heat transfer mechanisms: radiation from the flame, convection from the hot gases, and conduction from the heated refractory bricks. As the kiln rotates, the bricks absorb heat from the flame when they are exposed at the top of the rotation, and then transfer that heat directly into the material bed when they pass beneath it. This regenerative effect is essential for maintaining the high temperatures required for alide formation. To protect the steel shell from the extreme internal temperatures, a series of high-capacity cooling fans are positioned along the length of the kiln. These fans project a constant stream of ambient air onto the exterior of the shell, stripping away excess thermal energy. The temperature of the shell is monitored 24 hours a day by a specialized infrared scanner that travels back and forth along the length of the kiln. This scanner generates a hotspot map, identifying any areas where the refractory lining or the protective coating may have thinned. This level of technical oversight is a fundamental requirement of the manufacturing logic, as a shell failure would result in a catastrophic industrial event. Clinker emergence and the transition to the cooling phase. At the terminal end of the kiln, the material has completed its mineralogical evolution. It is now a mass of incandescent gray nodules consisting of approximately 65% alite, 15% bellite, and 20% of the aluminate and ferrite flux phases. The chemical identity of the limestone and clay has been permanently erased, replaced by a complex crystalline structure designed for hydraulic reactivity. As the clinker reaches the discharge lip, it falls out of the rotary kiln and into the clinker cooler. This transition is a decisive moment in the process. The clinker must be cooled rapidly to freeze the mineralogical state of the alite and prevent it from reverting back into bellite and free lime. The exit from the kiln characterizes a final burst of radiant heat and the percussive sound of the heavy nodules striking the cooler plates. The state of the minerals at the conclusion of this fourth chapter is one of functional climax. The geological aggregates have been synthesized into a new man-made mineral, possessing the latent chemical energy required to bind the structures of the modern world. The movement from the horizontal rotating domain of the kiln to the stationary air-swept domain of the cooler is the next logical step in the manufacturing cycle, marking the end of the burning phase and the beginning of the stabilization and final grinding sequences. The steady roar of the burner and the rhythmic rotation of the massive steel shell remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the thermodynamic discipline required to synthesize clinker from the raw minerals of the earth. The discharge of the incandescent clinker nodules from the rotating kiln into the entry chamber of the cooler represents the transition from the high-temperature synthesis phase to the stabilization and energy recovery phase. This stage is governed by the principles of forced convection and cross-flow heat exchange, where a high-velocity stream of ambient air is forced through a thick, porous bed of hot minerals. The clinker cooler, specifically the reciprocating grate variety, is a massive stationary steel enclosure containing a series of perforated plates arranged in a tiered manifold. The environment within the cooler is one of extreme thermal intensity and mechanical violence, characterized by the deafening roar of high-pressure cooling fans, the rhythmic clatter of reciprocating hydraulic drives, and the intense orange radiance of the cooling bed. The objective of this phase is twofold: to rapidly reduce the clinker temperature from 1,450 degrees Celsius to approximately 100 degrees Celsius, and to recover the maximum amount of thermal energy to be recirculated back into the manufacturing process. The clinker enters the cooler via a refractory-lined chute, forming a bed on the initial section of the grate plates. The thickness of this bed, typically maintained between 600 and 800 millimeters, is a critical variable in the cooling logic. If the bed is too thin, the cooling air will channel through the voids without effective heat transfer. If the bed is too thick, the pressure drop will exceed the capacity of the cooling fans, leading to red rivers of uncooled material. The movement of the bed is achieved through the reciprocating motion of the grate plates. Every second or third row of plates is connected to a high-torque hydraulic drive system that moves the plates back and forth in a synchronized sequence. This movement pushes the clinker nodules forward in a series of small, incremental pulses, ensuring a constant mass flow toward the discharge end. The dynamics of forced convection and aerodynamic cooling zones. The cooling energy is supplied by a battery of centrifugal fans positioned beneath the grate plates. These fans project ambient air into a series of pressurized chambers known as undergrate compartments. The air then passes through the perforations in the grate plates and upward through the hot clinker bed. The cooler is divided into several distinct longitudinal zones to manage the cooling rate according to the thermodynamic requirements. The quenching zone. Located at the very beginning of the cooler, this zone is subjected to the highest volume and pressure of cooling air. The logic of the quench is to reduce the temperature of the clinker as rapidly as possible to freeze the mineralogical state of the allied crystals. Rapid cooling prevents the tricalcium silicate from reverting into dicalcium silicate and free lime, a process that would significantly reduce the hydraulic reactivity of the final cement. This sudden thermal shock also induces microscopic cracks within the clinker nodules, which enhances their grindability in the final milling stage. The secondary cooling zone. As the clinker moves into the middle sections of the cooler, the air pressure is reduced and the focus shifts from quenching to steady-state heat extraction. In this zone, the thermal energy is stripped from the core of the nodules. The final cooling zone. In the terminal section, the clinker is brought down to a temperature suitable for transport on rubber belt conveyors. The air in this zone is often recycled or directed toward the primary dust collection system. The sound within the cooler department is a monolithic high-frequency roar, a combination of the high-velocity air movement and the mechanical vibration of the grates. The radiance gradually transitions from a brilliant white-orange at the intake to a dull matte gray at the discharge. The logic of thermal energy recovery and recirculation. The most significant technical advantage of the grate cooler is its ability to act as a high-efficiency heat exchanger. The air that passes through the hottest section of the clinker bed absorbs a massive amount of thermal energy, reaching temperatures of 800 to 1000 degrees Celsius. This heated air is not exhausted into the atmosphere, but is strategically recaptured for use in other parts of the facility. Secondary air. A large portion of the hot air from the quenching zone is drawn into the rotary kiln. This air serves as the primary oxygen source for the main burner, providing the thermal energy required to sustain the 1450-degree flame. By using preheated air, the kiln's fuel consumption is radically reduced. Tertiary air. A secondary stream of hot air is extracted from the cooler via a large-diameter refractory-lined duct and transported to the pre-calciner at the base of the preheater tower. This air provides the oxygen necessary for the combustion of the calciner fuel, ensuring the efficient dissociation of the calcium carbonate. This closed-loop thermal logic is a fundamental requirement of modern industrial sustainability, transforming a potential waste product, heat, into a vital technical resource. The management of the air balance is a complex task involving the adjustment of dozens of dampers and fan speeds to ensure that both the kiln and the calciner receive the exact volume of air required for stable combustion. The mechanical disintegration and the clinker hammer crusher. At the discharge end of the cooler, the stabilized clinker nodules must be reduced in size to facilitate efficient storage and transport. While most nodules are relatively small, some may aggregate into larger clods or snowmen during the sintering process. To address this, the cooler is equipped with a high-capacity clinker crusher, typically a hammer mill or a roller crusher. In a hammer mill, the clinker is struck by a series of heavy, high-chromium steel hammers rotating on a central shaft at several hundred revolutions per minute. The impact shatters the nodules against a stationary grate, ensuring that only material smaller than 25 or 30 millimeters passes through. The sound of the crusher is a rhythmic, percussive clack, a mechanical punctuation that marks the final physical reduction of the clinker. The material then falls onto a deep bucket conveyor or a high-temperature rubber belt, which transports it towards the clinker storage silos or a massive open-air storage hall. The filtration of exhaust gases and dust mitigation. Despite the high efficiency of the heat recovery system, a portion of the cooling air must be exhausted into the atmosphere to maintain the pressure balance within the cooler. This exhaust air is heavily laden with fine clinker dust and must be purified before release. This is achieved by the use of a high-specification electrostatic precipitator or a large-scale baghouse. In an electrostatic precipitator, the dust-laden air passes between a series of discharge electrodes and collecting plates. A high-voltage electrical field, often exceeding 60,000 volts, is applied, causing the dust particles to become ionized and migrate towards the collecting plates. At regular intervals, a mechanical wrapping system strikes the plates, causing the dust to fall into hoppers for recirculation back into the clinker stream. The level of environmental oversight ensures that the facility operates in compliance with strict particulate emission standards. The state of the minerals at the conclusion of this fifth chapter is one of functional stabilization. The incandescent nodules of the kiln have been transformed into a cold, hard, and chemically inert material, ready for long-term storage. The clinker now possesses the definitive mineralogical profile of alite and belite, protected by the rapid quenching of the cooler. The steady roar of the cooling fans and the rhythmic thumping of the hydraulic drives remain the constant acoustic backdrop of this industrial evolution, a testament to the scale of the thermodynamic and mechanical discipline required to stabilize the products of the fire. The movement of the clinker from the stationary domain of the cooler to the massive storage silos is the next logical step in the manufacturing cycle, marking the end of the thermal processing phase and the beginning of the final milling and additive sequence. Every ton of cooled clinker represents a concentrated reservoir of chemical energy, manufactured with a degree of consistency that ensures the reliability of the cement produced in the final stage. The progression of the stabilized clinker nodules from the high-capacity storage silos into the finish milling department represents the final mechanical transformation within the Portland cement manufacturing cycle. While the clinker possesses the definitive mineralogical profile of alite and belite, it is functionally inert in its nodular form due to a lack of available surface area. To achieve the hydraulic reactivity required for construction applications, the clinker must be pulverized into a sub-micron powder. This process, known as finish grinding, is governed by the principles of particle size distribution and the precise chemical integration of calcium sulfate. The environment within the finish mill is defined by a monolithic, high-decibel roar produced by the impact of thousands of steel grinding balls, the pervasive warmth of mechanical friction, and the rhythmic operation of high-efficiency air separators. The objective of this stage is to produce a standardized technical product with a specific surface area, measured as the Blaine value, that ensures a predictable rate of strength development and a controlled setting time. The process begins with the automated extraction of clinker and additives from their respective storage bins. The logic of the finish mill feed is based on a precise stoichiometric ratio managed by high-sensitivity weigh feeders that adjust the mass flow in real time. The primary components of the feed are clinker, which constitutes approximately 95% of the mixture for Type 1 cement, and gypsum, which is added at a concentration of 3 to 5%. In specialized applications, supplementary cementitious materials such as granulated blast furnace slag, fly ash, or natural pozzolans may also be integrated into the feed. This proportioning is a fundamental requirement of the manufacturing logic, as the chemical balance defines the eventual classification and performance grade of the finished cement. The mechanics of the two-compartment ball mill and grading media dynamics. The primary instrument of finish grinding is the horizontal ball mill, a massive rotating steel cylinder lined with wear-resistant manganese steel or high chromium plates. The mill is typically divided into two distinct chambers separated by a slotted diaphragm. The first compartment, this section is dedicated to primary crushing. It is loaded with large diameter steel balls ranging from 60 to 90 millimeters. As the mill rotates at approximately 15 to 20 revolutions per minute, the balls are lifted by the internal liners and fall with immense gravitational force onto the clinker nodules. This impact-driven comminution reduces the nodules into a coarse grit. The second compartment, the material passes through the central diaphragm into the second chamber, which is loaded with a much higher volume of smaller grinding media, typically 15 to 30 millimeters in diameter. In this zone, the comminution is achieved by attrition, the rubbing and sliding of the balls against the material. This produces the ultra-fine particle size required for high-strength cement. The sound within the milling hall is a continuous earth-shaking thunder, a manifestation of the massive kinetic energy required to decimate the crystalline structure of the alite. The logic of the two-compartment system is to maximize grinding efficiency by matching the size of the grinding media to the size of the material particles at each stage of the reduction process. The chemical role of gypsum and the regulation of hydration kinetics. The integration of gypsum, or calcium sulfate dihydrate, CaSO4.2H2O, is the most critical chemical intervention in the finish milling stage. Without the presence of gypsum, the aluminate phase of the cement, tricalcium aluminate, would react instantaneously with water upon mixing, leading to a phenomenon known as flash set, where the concrete hardens within minutes. Gypsum acts as a chemical retarder. When the cement is eventually mixed with water, the sulfate ions react with the tricalcium aluminate to form a microscopic layer of attringite crystals on the surface of the cement particles. This temporarily inhibits the hydration process, providing the necessary workability time for the transport and placement of concrete. The management of gypsum quality is absolute. If the temperature within the mill exceeds 110 degrees Celsius, the gypsum can undergo partial dehydration, transforming into plaster of Paris or hemihydrate. This can lead to false set, a condition where the concrete appears to harden prematurely but can be restored to a fluid state through further mixing. To prevent this, the mill is equipped with a high-capacity internal water cooling system and an external ventilation circuit that manages the thermal energy generated by the grinding process. Air classification and the closed-loop grinding logic. Modern finish milling operates as a closed-loop system, where the output of the mill is continuously sorted by a high-efficiency air separator. The logic of the separator is based on the aerodynamic behavior of particles in a rotating gas stream. The material exiting the mill is transported via bucket elevators to the top of the separator, where it is dispersed into a high-velocity air current. Coarse particles, fragments that have not yet reached the required fineness, possess too much mass to be carried by the air. They fall into the central cone and are recirculated back into the mill intake for further grinding. Finished cement, particles that meet the target micron specification, are carried through the separator vanes and collected in a series of high-capacity cyclones or bag houses. The fineness of the cement, expressed as the specific surface area in square centimeters per gram, is adjusted by varying the rotational speed of the separator cage. A higher speed results in a finer product with higher early strength, while a lower speed produces a standard grade cement. This metrological control is a study in industrial precision, as the Blaine value must be maintained within a very narrow tolerance to ensure consistency for the end user. The sound of the separator is a high-pitched aerodynamic whistle, a sharp contrast to the deep roar of the ball mill. The final transition and storage in high-capacity silos. As the finished cement exits the separator, it is a fine gray powder of exceptional chemical and physical uniformity. The temperature of the cement at this stage is often still elevated, requiring transport via air-cooled pneumatic slides or screw conveyors to prevent any thermal degradation. The cement is then directed into massive concrete storage silos, which can each contain tens of thousands of tons of material. The logic of the storage silo involves the separation of different cement grades, such as ordinary Portland cement, rapid hardening cement, or sulfate-resistant cement. The silos are equipped with specialized aeration systems that prevent the powder from compacting under its own weight, ensuring a smooth flow during the final loading and distribution phase. The environment at the top of the silos is one of monumental stillness, where the only movement is the slow, silent rotation of the level sensors and the occasional hiss of the dust collection system. The state of the minerals at the conclusion of this sixth chapter is one of total functional realization. The geological aggregates that began as limestone blocks in the quarry have been synthesized, sintered, and pulverized into a precisely calibrated technical instrument. The cement now possesses the latent chemical energy required to bind the world's infrastructure. The steady roar of the ball mill and the persistent hiss of the air slides remain the constant acoustic backdrop to this industrial evolution, a testament to the scale of the mechanical and chemical discipline required to manufacture a material that is the literal foundation of modern civilization. The movement of the finished cement from the storage silos to the bulk loading docks and the automated bagging plants is the next logical step in the manufacturing cycle, marking the end of the fabrication history and the beginning of the logistical deployment to construction sites around the globe. The transition of the finished powder from the high-capacity storage silos to the logistical deployment phase represents the final sequence in the industrial life cycle of Portland cement. While the material has achieved its definitive chemical and physical identity within the finish mill, it must undergo a rigorous protocol of quality verification and automated packaging before it can be integrated into the global infrastructure. This phase is governed by the principles of statistical quality control and high-velocity pneumatic transport. The environment within the shipping and packing department is defined by the sterile electronic hum of laboratory instruments, the percussive sound of automated palletizers, and the constant hiss of pressurized air systems. The objective of this terminal stage is to ensure that every ton of cement meets the absolute standards for compressive strength, setting time, and chemical stability while maintaining a seamless flow of material to the construction market. The process of quality verification begins in the centralized laboratory, where samples are automatically extracted from the conveyor stream at regular intervals. The logic of this testing is to provide a comprehensive profile of the batch's performance. The primary metrological procedures include X-ray diffraction, XRD analysis. This instrument utilizes the diffraction of electromagnetic waves to quantify the crystalline phases within the cement. The system measures the exact concentrations of alite, baelite, and tricalcium aluminate, ensuring that the mineralogical synthesis of the kiln was successful and consistent. Compressive strength testing. Technicians prepare standardized mortar cubes using a precise mixture of cement, sand, and water. These cubes are cured in a humidity-controlled environment for specific periods, typically 2, 7, and 28 days. After curing, the cubes are placed into a high-capacity hydraulic press and crushed to determine the exact force required for failure. Blaine fineness verification. An automated air permeability apparatus measures the specific surface area of the powder. This value is critical as it determines the hydration rate. A deviation of even a few square centimeters per gram would alter the performance of the concrete on the job site. The mechanics of bulk loading and pneumatic conveying systems. The majority of the produced cement is distributed via bulk logistics, utilizing specialized tankers, rail cars, or maritime vessels. The movement of the powder from the silos to the loading spouts is achieved through a network of high-capacity air slides and pneumatic screw pumps. The logic of pneumatic conveying is based on the fluidization of the material. By injecting compressed air into the material, the cement behaves like a low-viscosity fluid, allowing it to be transported through enclosed pipelines with minimal mechanical wear. At the loading dock, the cement is gravity-fed through a telescopic loading spout into the hatch of a bulk tanker. These spouts are equipped with integrated dust extraction systems that maintain a vacuum at the point of discharge, preventing the release of fine particles into the atmosphere. The mass of the material is monitored by high-precision weigh bridges that communicate directly with the plant's logistical software. The sound in this area is a rhythmic, low-frequency roar produced by the movement of the powder through the steel pipes and the constant hum of the vacuum collectors. A single bulk tanker can be loaded with 25 to 30 tons of cement in less than 10 minutes, a testament to the efficiency of the automated transport logic. Automated bagging and the logic of the rotary packer. For the retail and smaller scale construction markets, the cement is processed through an automated bagging plant. The core of this operation is the rotary packer, a sophisticated machine consisting of a rotating turret with multiple filling spouts. The packaging material, typically multi-wall valve bags made of high-strength craft paper and plastic liners, is fed into the machine by a robotic applicator. As the turret rotates, each bag is fitted onto a spout and a calculated volume of cement is injected using high-pressure air. The filling process is controlled by a digital weighing system that ensures an accuracy within a few grams. Once the target weight, typically 25 or 50 kilograms, is achieved, the valve of the bag is automatically sealed by the internal pressure of the material. The sound of the bagging hall is a percussive, high-frequency sequence of air discharges and mechanical clicks. The filled bags are then transported via a conveyor belt to the automated palletizing station. Here, a robotic arm organizes the bags into a stable, interlocking pattern on a wooden or plastic pallet. The entire pallet is then moved to a stretch hooding machine, which applies a high-tension plastic film that encapsulates the cement, protecting it from moisture and mechanical damage during transport and outdoor storage. This level of protection is essential, as even a microscopic amount of atmospheric moisture would initiate the hydration process and ruin the product. As the cement leaves the facility, it enters the terminal phase of its industrial journey, the creation of concrete. When the powder is eventually mixed with water, sand, and coarse aggregate at a construction site, the latent chemical energy within the alite and baylite is released. This process of hydration creates a crystalline network of calcium silicate hydrate that binds the aggregates into a man-made stone of immense durability. The logic of this transformation is one of permanent structural realization. The molecules that were once quartz and limestone in a quarry have been broken, synthesized in a fire of 1,400 degrees, and pulverized into a fine dust, only to be reconstituted as the skeletal frame of a bridge, a skyscraper, or a dam. Over decades, the concrete will slowly reabsorb carbon dioxide from the atmosphere, a phenomenon known as carbonation, which effectively mimics the natural geological cycle of the limestone from which it originated. The life cycle of the silicate substrate is thus a closed loop of geological and industrial force. The steady roar of the plant's fans and the rhythmic thumping of the logistical machinery remain the constant acoustic backdrop to this evolution, a testament to the scale of the precision required to engineer the foundations of the modern world. Every square centimeter of the finished concrete represents a triumph of thermodynamic and mechanical discipline, a standardized solution for the protection of human life and the endurance of civilization, manufactured with a degree of consistency that ensures reliability across billions of individual installations.